Alright, this is part 2 of the lesson on rational equations and inequalities. So in this part of the lesson, we're going to focus on solving rational inequalities. Things that look like this. We have a left side and a right side separated by this inequality symbol. It could be a less than or a greater than symbol. So when you're ready to get started with this part of the lesson, make sure you have the copy of the blank lesson from jensenmath.ca. You can find it in the Advanced Functions course. We are in Unit 6, and this is the first lesson. And in this lesson, we've already completed parts 1 and 2 in a previous video. So what we're going to be doing in this video is completing part 3, solving rational inequalities. So let's get started. Okay, so we're going to solve a few rational inequalities together. Here's the 4 that we're going to solve together. Before we start solving those, I want to remind you about what we know about solving inequalities from when we solved polynomial inequalities earlier in the course. So we learned when solving polynomial inequalities that we could solve them just like equations as long as we followed one rule. When both sides of the inequality are multiplied or divided by a negative number, we had to reverse the inequality sign. So that was an easy rule to follow if we were solving a linear inequality. That was fine. But if we got higher degree inequalities, like degree 2, degree 3, or so on, we figured out that it might be easier to solve them if we solve them graphically or by making a factor table. So what are we going to do for these types of inequalities? Well, we're not going to try and solve these algebraically like equations and then try and follow that rule of reversing the inequality when we multiply or divide by a negative. We're not going to do that because if I multiplied both sides of this inequality by x plus 1 and x minus 3 to try and get rid of the fractions, do I have to reverse the inequality? Did you just multiply by a negative if we multiplied both sides of this by x plus 1 times x minus 3? Well, is x plus 1 negative? Sometimes, depends on the value of x. And is this negative? Sometimes, so it depends on the value of x. So we would have to split our algebraic solution into different cases. Depending on the value of x, we might have to reverse the inequality. And the process gets pretty complicated pretty quick. So we're not going to solve it algebraically. So maybe we'll solve it graphically. We could. We could figure out what the graph of this looks like and the graph of this looks like, and then figure out when is the one on the left greater than the one on the right. But that would be fairly complicated as well to generate those graphs and get exact values where we know that the one on the left is greater than or equal to the one on the right. So I think the most efficient thing to do is to make a factor table. So let's go over how we're going to make a factor table. So before we make the factor table, we're going to follow these steps. We're going to start by moving all of the terms to one side. After we do that, we're going to combine the terms by getting a common denominator. And then we're going to factor everything as much as possible, and then make our factor table, sometimes also called a sign chart. And how do we make a factor table? I'll reference these steps as we actually do the questions, but I'll just go over them quickly now. In the factor table, we use the x-intercepts and vertical asymptotes, I'll explain why in a little bit, as our dividing points. And then we choose a test point within each interval between the x-intercepts and vertical asymptotes. And then we plug those test points into all of the factors of the polynomial and the inequality to see whether it's positive or negative, and that'll tell us whether it's greater than or less than 0 within each interval. So those steps may seem a little bit overwhelming, just me reading them over, but let's give a question a shot and see how they work. So this first one, all of the terms are already moved to the left. On the right side of the inequality is just 0. So step 1 is done, everything's already moved over. Step 2 says combine everything and write it as a single fraction. Well, this is already written as a single fraction, already done for us. So the first 2 steps of this one are already done. Step 3 is factor it. So in the numerator, I have a quadratic where the a value is 1, so I can just find a product of 5 and a sum of 6, and that's x plus 5 times x plus 1. In the denominator, the quadratic has an a value that is not 1, so I would have to find 2 numbers that have a product of a times c, so a product of 6 and a sum of negative 7, and those 2 numbers are negative 6 and negative 1. Now there's a bunch of shortcuts to use those numbers to come up with the factors, but I'm just going to off to the side, do it the long way by decomposition. Okay, now that I've figured out the factors, I can write them over here. It's x minus 3 times 2x minus 1. And I'm interested in when is this less than 0? So you might be wondering, okay, well, why did we bother factoring this? Well, it's important to get this factored because from the factored form version of this polynomial, I could figure out where this function's x-intercepts and vertical asymptotes are. And those are going to be the important points of this function to help me figure out when it is going to be less than 0. Let me start by finding the x-intercepts and vertical asymptotes, and then show you a graph of this, and hopefully you'll be able to make the connection as to why we're finding them. So an x-intercept is an x value that would make the y value be 0. So what value of x would make this whole thing become 0? Well, what makes a fraction be 0 is if the numerator is 0. So how could the numerator of this be 0? So the x-intercepts are at x values of -5 and -1. And where are the vertical asymptotes of a function? The vertical asymptotes are at x values that make the denominator be 0. So what would make the denominator of this become 0? X cannot be 3 or a half. So I have two vertical asymptotes. They would be at x equals 3 and x equals a half, because those two values make the denominator of this become 0, which means this whole rational function would be undefined. So now that I have the x-intercepts and the vertical asymptotes, I can actually figure out when the function is going to be less than 0 by carefully choosing some test points and setting them up in a factor table. Let me actually backtrack a bit and show you the graph of this so you can hopefully understand why we're doing this process. So here's the graph of the function. We're interested in when is this function less than 0. That's what our original inequality says. It says when is it less than 0. So looking at the graph, we're looking for when is the function below the x-axis. When does it have negative y values? Well, I have Desmos calculating the y values for me for any value of x, and I'm just going to drag this purple point along so you can see at that purple point it's calculating the y value for me. So before the x-intercept of -5, notice all those y values are positive. But after the x-intercept of -5, the y values become negative. So at the x-intercept of -5, the function switched from being positive before to being negative after. And then at the x-intercept of -1 is the place where it switches back from being negative before to positive after. So it's easy to see that, of course, at an x-intercept, that's a place where a function might switch from being positive to negative or vice versa. So x-intercepts are crucial dividing points that we might want to test between to see if the function is positive or negative, to see if that interval is an answer to our inequality. We're looking for intervals that output values that are less than 0. So right now, based on what we've looked at so far, the interval between -5 and -1 is a solution to our inequality. Any x value between -5 and -1 yields a negative y value, so a value less than 0. But the function can also switch from being positive to negative around vertical asymptotes, right? After the vertical asymptote of a half, the function jumps way down here to this other part. So it was positive y values up here. After the vertical asymptote, it jumped way down here, and now it has negative y values. So vertical asymptotes are other important dividing points where the function could switch from being positive to negative or vice versa. And then once it gets to the next vertical asymptote at an x value of 3, it jumps back up to being above here, where the y values up here are positive again. So we're looking for when is the function less than 0. If we have the graph, we can see it's between -5 and -1, and also again between a half and 3. So there are two intervals where the function is less than 0. How are we going to get that algebraically? We're going to use these as dividing points in our factor table. So let's set up the factor table. Okay, so I very carefully picked how many horizontal and vertical lines to have here. Let me explain how I chose each of those amounts. So the vertical lines are the dividing points for our intervals. We'll always put -infinity on the left, positive infinity on the right, and then I needed a vertical line for each of the x-intercepts and for each of the vertical asymptotes. And make sure we write them in ascending order. So -5, then -1, then a half, then 3. And then how did I decide how many horizontal lines to have? Well, I needed a section for each of these 4 factors. So I'll put the factor of x plus 5 here, x plus 1 here, x minus 3 here, and 2x minus 1 here. So now I need to figure out, within each of these 5 intervals, is the function positive or negative? We're interested in, when is it negative? When is it less than 0? And we know at these x-intercepts or vertical asymptotes are the only places where the function might switch from being positive to negative, or vice versa. So I need to pick a test point within each interval. So I need to pick a number between negative infinity and negative 5. I'll choose negative 6. And now I need to see this function at an x value of negative 6, is it positive or negative? So what I'm doing is I'm going to test this value in each of those factors separately. In x plus 5, I would get negative 6 plus 5, which is negative 1. It's a negative result. I don't actually care what the result is, I just care the sign of it. And I'll explain why in a second. Plug negative 6 into this factor, I get a negative result. Negative 6 into this factor, negative result. Negative 6 into this factor, negative result. So negative 6 into this whole thing would give me a negative times a negative, which is positive, divided by a negative times a negative, which is positive. So I'd have a positive over a positive, so the overall result would be positive. So the function before an x value of negative 5 is positive. And if we look at that graph that I showed you, before an x value of negative 5, the function is above the x-axis. It's positive. How about between those x-intercepts of negative 5 and negative 1? I'm going to pick a test value of negative 2 and test it in each of the factors. Negative 2 plus 5 is positive 3. Negative 2 plus 1 is negative 1. Negative 2 minus 3 is negative 5. And 2 times negative 2 minus 1 is negative 5. So it's negative. So in this factored form version of the polynomial, I would have a positive times a negative over a negative times a negative. That would be an overall negative result. An odd number of negative factors results in a negative result. An even number of negative factors results in a positive result. And now let me just complete these 3 columns as well, following that same pattern. Okay, now that the table is complete, all we're going to be looking at to answer the question is the bottom row. So the original question says, when is the function less than 0? We know the function will be less than 0 whenever the overall value of this is negative. So in this interval, and again in this interval. So we can answer the question now. So answer. The original inequality is true if we have an x value between negative 5 and negative 1, or if we have an x value between 0.5 and 3. Now we can write this in 2 ways. We could write it like that with inequality symbols, or we could write it in interval notation. So I could say x is an element between negative 5 and negative 1, or 0.5 to 3. All right, let's try another one. We'll try 2 more together, and then I'll leave the 4th one for you to try on your own, but I'll still show you the solution in this video. So part B, to solve this inequality, resist the temptation to multiply both sides by x, right? Because then we don't know if we have to reverse the inequality or not. We have to split it into multiple cases, so don't multiply both sides by x. What we want to do instead is move all of the terms to one side using inverse operations. So we'll just subtract this term to the left side of this inequality. So I'll have x minus 2 minus 8 over x is less than 0. So all of the terms are now on the left side of this inequality. What I need to do now is figure out what the x-intercepts and vertical asymptotes of this are. And the easiest way to do that is to combine all of these as a single fraction. So I need a common denominator. So right now, these 2 terms are both over 1. So a common denominator between these 3 terms would be x. So I would have to multiply top and bottom of this one by x, and top and bottom of this one by x. And then they would all have that same common denominator of x. And you might be saying, well, I thought we weren't allowed to multiply by a variable. Well, x divided by x, that's just 1. We're really just multiplying by 1, so we're allowed to do that. So what I have here, x times x is x squared. So I have x squared minus 2x minus 8 all over that common denominator of x. And we want to know when is this less than 0. So we're wondering when is this negative. So what we need to do now is we need to figure out, well, where might it switch from being positive to negative, and then test values within those intervals. So where might it switch? It might switch at x-intercepts or vertical asymptotes. So to find those, we should factor this numerator. So the numerator would factor to x minus 4 times x plus 2, because negative 4 and 2 are the numbers that multiply to negative 8 and add to negative 2. And this is all over x. So we need to list the x-intercepts and the vertical asymptotes for this rational function, because if we can figure those out, then we can test values between them and figure out when the function is going to be negative, when it's going to be less than 0. And that's what we're trying to solve for. So what are the x-intercepts? Well, x-intercepts have y values of 0. So what would make this whole thing become 0 is whatever would make the numerator become 0. So how could the numerator be 0? Well, if x was 4 or negative 2. And vertical asymptotes. Well, vertical asymptotes occur at x values that would make the denominator become 0. So what would make this denominator become 0? Would be 0. X can't be 0. If x was 0, we'd have negative 8 over 0. That's undefined. So these three values are the dividing points. These three values are the places where the function might switch from being positive to negative or vice versa. Now we don't have the graph of this function, but let me show it to you just so you understand what we're talking about. Okay, here's the function. It's an interesting function. It has a vertical asymptote and this slant asymptote here, also called an oblique asymptote. But we don't really care about being able to generate the graph. I'm just showing you this so we can see why we found the x-intercepts and vertical asymptote. Notice the function is negative before the x-intercept of negative 2, and then positive after. So that x-intercept is a place where it switches signs. And then it's positive forever, it appears, until it gets to the other side of the vertical asymptote. Then the function reappears down here with negative y values. And then it switches from negative y values to positive y values after this x-intercept right there. So those two x-intercepts and this vertical asymptote are the places where the function can switch signs. So we just need to test values within each interval. The interval before negative 2, between negative 2 and 0, between 0 and 4, and between 4 and infinity. We test where the function is in each of those intervals, and then we can figure out the answer to our inequality, which wants to know when is it less than 0, so when is it negative. So we'll make our factor table, so we'll draw those horizontal and vertical lines again. I chose 5 vertical lines because I need one for negative infinity, positive infinity, and then each of these 3 values, making sure to put them in ascending order. So negative 2, 0, 4. And then I also need a row for each of the factors. So I need a row for x minus 4, for x plus 2, and for x. And at the very bottom, I'll state the overall sign of this rational function here. So I need to now pick a test point within each of these intervals. So I'll pick a test point between negative infinity and negative 2, a test point in this interval, in this interval, and in this interval. And these test points, remember, these are x values we're choosing. We're choosing x values to plug into this to see if it's positive or negative. If it's negative, well, a negative number is less than 0, so that will be an answer to the inequality. So instead of plugging into the whole thing and evaluating, I'm just going to plug it into each factor one by one. So plug in negative 3 to x minus 4, that's a negative result. Negative 3 into x plus 2, negative 3 plus 2 is negative 1, so that's a negative result. And negative 3 in for x is, of course, negative. So I figured out I would have negative times negative divided by negative. That's a negative result. Odd number of negative factors is a negative result. So let's follow that same process for these 3 intervals. Okay, now that we have the factor table complete, all we have to do is look at the bottom row and look for when is it negative, because our inequality is asking when is this less than 0. So it's less than 0 whenever it's negative. It's negative in that interval and in this interval. So I could write that in 2 ways. As inequalities, I could say x less than negative 2, or between 0 and 4. Or I could write it in interval notation. I could say x is an element between negative infinity and negative 2, or between 0 and 4. Either way of expressing your answer is fine. Let's just compare that to the graph and make sure we found the right intervals. Notice the function is less than 0 when x is less than negative 2, and again between 0 and 4. The function is down here, it's negative. So we found the correct two intervals. Part C, once again, resist the temptation to cross multiply. We don't want to be multiplying both sides by any variables. So instead, we're just going to move this whole term to this side of the inequality. So we're going to subtract it over. So I have x plus 3 over x plus 1 minus x minus 2 over x minus 3 is greater than or equal to 0. Oh, this is the first time that we have an equal sign underneath our inequality. The only time we really have to consider that is when we're expressing our final answer, and I'll talk more about that when we get there. But for now, let's follow the same steps we did for A and B. Now that we have everything on one side, let's get a common denominator. So I would need to multiply this one top and bottom by x minus 3, and this one top and bottom by x plus 1. Now you should notice they both have a common denominator, x minus 3 times x plus 1. So I can write this as a single fraction. X minus 3 times x plus 3 minus this product, x minus 2 times x plus 1, all over that common denominator, x minus 3 times x plus 1. And we want to know, when is this greater than or equal to 0? To figure out when is it greater than or equal to 0, I'm going to have to find the x-intercepts and vertical asymptotes, and then test points within the intervals. Before I can find the x-intercepts, this up here is not in fully factored form. There's this minus sign here. So what I'm going to have to do is expand this and collect some like terms, and hopefully through that process be able to find what the x-intercepts are. So this is a difference of squares. That would be x squared minus 9 minus, make sure you put this product in brackets so that we know we have to subtract the whole product. So this product would be x squared plus x minus 2x, that's minus x, minus 2. And this is all over that common denominator. Now I can subtract all three of these terms. So I have x squared minus 9 minus x squared plus x plus 2. Collect like terms in the numerator, x squared minus x squared, those cancel out, that's 0. And I have an x and a negative 9 plus 2, that's negative 7. Okay, so now it should be obvious what the x-intercepts and vertical asymptotes are. X-intercepts are x values that make the numerator become 0. So the only x-intercept is at an x value of 7. And the vertical asymptotes are x values that make the denominator be 0. So x can't be 3 or negative 1. Either of those would make the denominator 0, making this whole rational function undefined. So these three values are the places where the function might switch from being positive to negative. So we'll use those as dividing points and test x values within each of the intervals. In this question, we're interested in when is the function greater than or equal to 0. So when is it 0 or positive? So let's set up our factor table. So once again, far left is negative infinity, far right is positive infinity, and then between those two, I need each of these three values in ascending order. Negative 1, 3, 7. And then I need a row for each of the factors, x minus 7, x minus 3, and x plus 1. And now I get to choose my test values for x within each interval. Your test values don't have to be the same as mine. Just pick any number between negative 1 and 3 and put it there. I just chose 0 because I thought that was an easy number to work with. Okay, now let's test each of these numbers in this whole rational function by plugging into each factor one at a time and seeing if we get a positive or negative result. Negative 2 minus 7 is negative 9, negative 2 minus 3 is negative 5, and negative 2 plus 1 is negative 1. So I would have a negative divided by a negative times a negative. An odd number of negative factors is an overall negative value. So the interval between negative infinity and negative 1 is not a solution to the inequality. The function is not greater than or equal to 0 there. It's less than 0 there. How about in this interval, negative 1 to 3? Let's plug 0 in for each of them. And I get a positive result. Good, I found one interval that is a solution to my inequality. I now know it's greater than 0 between negative 1 and 3. How about this interval? So this interval is not a solution, it's negative there. And how about this interval? This interval is also a solution because it's positive there, right? We're interested in when is it greater than or equal to 0. So we're interested in when is it positive. It's positive there and there. So when we describe our answer, we have to be careful that we include not only the intervals where the function is greater than 0, but also the places where it's equal to 0. So we have to make sure that we include 7 in the answer, because at 7, this whole thing is 0, and we want to include that in our answer. So let's watch how we do that. So between -1 and 3, the function is positive. So in our answer, we'll say x is between -1 and 3. And when x is greater than 7, so we'll say or x is greater than 7. But I need to include 7 in my answer, because that is a place where the function actually equals 0. So how do I include it? I put an equal sign under there as well. It says when x is greater than or equal to 7. No equal sign under these two, because at -1 and 3, the function is undefined. So that's of course not an answer to when it's greater than or equal to 0. So how could I write it in bracket notation? I would say x is an element of -1 to 3 or 7 to infinity. And I was very careful to put a square bracket at 7 to make sure that shows that it's included in the answer. Round brackets at -1, 3, and infinity, because those are not included in the answer. Okay, we've done 3 examples together. I think it would be a good idea now if you were to pause the video and try this one on your own. And then after you give it a try, unpause and see how you did. I'll show the solution. Now, this one is probably the most difficult of the 4, so don't get discouraged if it takes you a little bit of time or if you don't get it right. Just follow along after and fill in the proper solution. So pause now and give it a try. Okay, so here's the solution. Just follow along. Alright, that's it. Hopefully you were able to get the right solution there. It was a little more difficult because we had a degree 3 polynomial up here we had to factor, but we could do it by grouping. And then also, hopefully you figured out what the x-intercepts were and that there actually were no vertical asymptotes for this one. And these are our final solutions. So make sure you go to jensenmath.ca and get those practice problems and try them out. So that's it.